Alrighty, thank you so much for your time this evening or this morning or whenever you're watching this. My name is John Beggs. I'm in MA 383. I'm a cadet at the United States Military Academy. And I'm here today to talk to you about proofwriting, the proofwriting process, different steps that we've learned in MA 383, in addition to my own midterm proof. So I really love MA 383, but if you're new to this and you're not from the course, you're not in this course right now. MA 383 is MA 383 Foundations of Math. It's a part of the honors track of the Applied Statistics and Data Science major here at West Point. I'm lucky enough to be an ASDS major and hopefully pursue a career in the Army similar to data science and maybe becoming a statistician later on in life. Who knows? But yeah, I absolutely adore it. And MA 383 is a requisite for completing the honors track, which also entails a research thesis. And it's been an incredibly important class thus far, especially when thinking about how we think about math and how we go about solving math problems. So MA 383 really gives us a look under the hood of a lot of different things that we didn't look at beforehand. I'm going to get to a few examples of that here in a little bit, but really just keeping in mind about MA 383 that the way the course is structured is about proofwriting. And we're here to prove things in math that may seem self-explanatory, but it's really important to getting a better understanding of mathematical concepts that we've genuinely taken for granted since we learned them. So it's not just about disks and washers or small algebra anymore, or integrals or whatever else. It's about getting under the hood of number theory, which we're going to get to soon, combinatorics, set theory. All of this is part of MA 383. And we get the opportunity to do some really great proofs and cool proofs of those concepts. So when I first realized I was going to have to take MA 383, I was a little bit nervous because I didn't really know what a proof was. My only exposure to proofs before this was in 7th or 8th grade geometry whenever I took it. And I would have a little T table, and I'd have my if and I'd have my then, and it would be, a random thing, and then I had a prescribed series of definitions and theorems that I could use from this list, and that's what we would do on tests. It was, it's kind of similar to what we do now, except we're really looking at different ways to prove kind of basic things, which isn't necessarily the same as previous proofwriting I've done. So my point is, MA 383 was my crash course in proofwriting and actually learning what proofs are. So what I learned, a proof is a mathematical, it's a way that mathematicians show things to be true. It's a way to prove that something is true, a mathematical concept, a conjecture, a statement, something in math that is true. Obviously, it doesn't necessarily have to be math, but it's a form of mathematical logic, I would say is the best way to put it. And we use it in our field in math to show why the world is the way that it is and why numbers interact with one another the way that they do. And it's been a great process just to learn what we do it for and why we do it. So, like I said, I was really nervous to start writing proofs. I didn't know what I was getting myself into. I was actually an English major originally, and I switched to math kind of on a whim. Switched to data science kind of on a whim. And this was a pure math class involved with the major that I was nervous for. So how do you succeed in something you've never done before? That's a question I had to ask myself several times before kind of getting into MA 383, and I'll ask it again several more times before my time here at West Point is finished. But how do you succeed in something you've never done before? Well, the answer I've found is pretty universal for anything you haven't done before, is you just got to put in the reps. And that's something we learn on day one in MA 383 is you're not going to get good at this if you don't go through the growing pains of doing it. So when you're working on your homework, when you're working on your proof for your homework or whatever else it is, I've found that if you don't put in the reps, you're not going to see any rewards later on. Whenever you're given less guardrails, whenever the training wheels are taken off, you're not going to know what to do with yourself if you haven't put in the reps and done the work to know the definitions and to know how they interact with one another, and to know mathematical symbols and terms. Because a lot of cows, especially that haven't taken super advanced math classes, we're not as familiar with symbology yet. And so this is a crash course and all that, and you got to put in the work. The great thing is that it's a very accessible community. So whether it's your instructor, for me it's Dr. Thomas, but it's an accessible community in that people want you to learn this. We want to help each other out, and I'm kind of excited to be a part of that now that I've started to put in the reps and do the work that it takes to get better at writing proofs. So yeah, how do you succeed in something you've never done before? You just got to do it, and that's kind of why this was such a different class. I've taken so many math classes at this point. I've taken 2 years of college math already. I've taken advanced math. I took math in high school. I took it in elementary school, middle school, etc. We've been doing math forever. But what makes writing proofs different? Well, it's difficult to explain, so it's better if I just show you. Here's the difference. So on the left side, you'll see here that just a random, like a problem that you'd get in like 6th, 7th grade algebra, right? Where you have to just solve for x, and you divide by both sides, and then you get your final answer. And yes, you get your final answer. That's just basic algebra. There's really not a lot going on under the hood there that we can see yet. I know there is, but we can't. And then if you look at the right, this is the problem that we got on the first day of MA 383. And Dr. Thomas said, prove that there are an infinite number of prime numbers. Well, what? Like, what are you talking about? Prove that there are an infinite number of prime numbers? Well, just thinking about it without actually looking under the hood, it kind of makes sense that there's an infinite number of prime numbers. I mean, we know that infinity exists, right? I guess I haven't proven that, but we're assuming that infinity exists just in our everyday life. And we know that there are prime numbers that go up really, really high. But are there an infinite amount? And so that's why you write a proof, is to prove that this is a statement that is true. So we walked through it on the very first day, and it was astounding to see the process and how it goes. So, like I said, don't we already know that there are an infinite number of prime numbers? Not quite. So here's how we started out. The first proof that we ever did, we assumed on the contrary. That's one of the steps. That's a strategy you can take when writing a proof. Assume on the contrary that there's a finite number of primes. Why do you assume on the contrary? Well, the point is, then at the end, you can say the opposite if you find the opposite to be true, which is being a contrarian in this example is very, very important. Mathematics, being a contrarian is a very, very good thing I've found thus far when you need to prove, when you need to assume on the contrary for a proof. And like I said, this was the very first day, and Dr. Thomas just takes off. Assume on the contrary that there are a finite number of primes. Well, then that means we can list them. And then you can see how the rest of the proof goes on, but I really want to point out here, I've kind of left out a few of the little steps, but I've gotten the big stuff, and I want to point you to the fundamental theorem of arithmetic and how that leads to your conclusion that P sub I must be 1 or negative 1. And then the next line is, but that's impossible because 1 and negative 1 are not prime. So what I found so interesting about this exact moment in the class, and this, like I said, this was the first day, what I found interesting is that you know that 1 and negative 1 are not prime numbers, right? No. You don't know that, right? Like, that doesn't make a lot of sense. Then you have to get into the definitions of primes, and you have to get into all of the things that go under the hood of what the primes are. And then eventually you arrive at your assumption being false, and that there are, in fact, an infinite number of primes. Just as you thought, but now you know how to prove it, right? Another really great example of a proof that really, got me excited about the class was actually a homework assignment. And it was in the combinatorics block. And it was talking about if you have the soup, if you have here at West Point, we have a superintendent, right? And if you wanted to put cadets up on stage with the superintendent while a guest speaker is talking or something like that. And the soup obviously is going to be the one closest. So I've got the soup here in blue. And if you want to arrange cadets so that they're sitting next to them, right? How many ways can you organize the cadets on stage next to the soup, right? So we go through the proofwriting process, which I'm going to get to in just a little bit, but the point is, I have this conjecture at the beginning that I start off with. If there are n cadets, then there are n factorial ways to organize them. And as I'm doing this proof, as I'm going through the steps that you see, I'm basically going to myself, I'm thinking about it like almost as if there's a picture. I see General Gilland up on stage, and I see the cadets in the problem sitting right next to him, and how many ways could I put them? And eventually you arrive at the answer. But this is an example of how proofwriting is not like regular math. If you just tell me to solve for x when 6x equals 24, I don't see that, right? Like there's no picture involved. There's no way to look for something involved in it. This was a specific example where you can really see the answer, you not necessarily see the answer, but you can see the different variations, and you can see how those are all embedded within the answer that you end up getting. And we eventually are able to prove that there are, in fact, n factorial ways to organize the cadets up on stage next to the superintendent. So, yeah, that, like I said, that was a personal favorite of mine. And it would lead me to my next point, which is pretty fascinating. And this is something that my instructor brought up early on in the class, is that when we write proofs, this is another way that it's different from, when it's different from just normal math or regular math that we've done in the past. When you write a proof, you leave behind personality residue. And personality residue is an idea that we all leave behind bits of ourselves in what we write. And of course, this is going to be the same for maybe how you write something, but maybe not what you write. So, for example, if I take you back to this slide and this slide, these two are actually proofs that I wrote in class and or for homework. And I will tell you that they're not that different from the way that I wrote them in my notebook. We write all of our proofs handwriting in a black marble notebook. But the way my brain thinks is kind of a step by step, and I like to indent, and I like to kind of make sense of things in what I think is a logical manner. That is personality residue. It's the way my brain works. You can kind of see it in the way that I walk the reader of my proof through what I've actually tried to show. That's just another great example of how writing proofs is so much different from regular math that we do leading up to MA 383. So how do we actually get to doing this, though? How do we actually start? Well, in MA 383, we're given a proofwriting wiki, like a Wikipedia page, basically. It's a note, it's a piece of paper, but a proofwriting wiki for how we do it. So there's a step, and so what I'm going to do is I'm going to walk you through the steps and the purpose of that individual step. So first, we develop examples. We like to say kicking the tires in MA 383. So basically, we kick the tires and we develop numerical examples for the proof that we're trying to do eventually. So we choose an example that satisfies the hypothesis, we choose one that doesn't, and we show that the example we're developing is valid or not valid. Not valid is really important because then you're going to actually end up providing a counterexample, or you're going to be looking for something else that falls within the confines of the problem. I'll show you that in my proof in just a bit. So that's step one. It's very important. Step one is the bulk of your work when it comes to the step-by-step guide. I try to have at least 3, 4, 5 examples for whatever proof I'm working on. And that leads me to step two, which is the if-then statement. So this is kind of the bread and butter of the proof, I would say. It's I guess more of the bread and butter in that this is what you're actually going to prove. So it can be revised later with the show and no, which I'll talk about in a sec as well, but it's really the basis for the proof. This is what you get started on. Step 3, write down the know. What's the know? What do I know? Well, what I know is the words between if and then in the if-then statement. So if blank, then blank. Well, I want that first blank. That's my know. That's the thing that I know is happening because I've given it the modifier if, and I've given it the word if before it. So that's what I know. And so after that, I really want to expand it because, just having that by itself doesn't mean anything. So I got to expand it. I got to provide relevant information for my know. I've got to provide theorems, definitions, formulas, and I've got to prioritize using symbols and expressions that can be manipulated later on, because that's going to let me actually write the proof, the clean version of the proof, whenever it gets to that time. And I'm going to do this same process for steps 5 and 6 with my show, which is what I'm actually going to try to show in my proof. So that's the word after then. So if blank, then blank. That's my second blank. And so I want to expand that the same way I did the know, with the relevant information. And I also want to be able to use symbols and expressions that can be manipulated later on. The final step in this proofwriting guide is the second draft of your if-then statement. So sometimes this doesn't change, right? There have been a lot of instances where this hasn't changed for me. And the proof I'm going to get to in just a second is one of those examples. However, this lets you know where to start and where to stop. It's really kind of think of it like a launching pad for you to really get into writing your clean proof. I kind of pointed out, use it as a first sentence and last sentence of the proof. I personally think of, sometimes I think of writing proofs in terms of writing code. So, Like I use first sentence and last sentence in this example is like if you're writing an F string in Python, first sentence, last sentence, where are these? Those are obviously going to be your first and last in your proof, but you got to find what's going to be in between them. And that's where it starts with let X or assume Y. That's your expanded no from your previous steps. And then the next bit is often I'm going to show. I want to tell my reader what I'm going to show and what direction, what journey I'm going to take them on. So that gets me to the proof that I was given for the midterm right now. So my most recent proof, and I was given conditions set by Dr. Thomas. So the power sets of a set are the set of all subsets of a set. For example, if A equals the set 1, 2, then the power sets of A denoted by P of A equals the null set, the empty set, the set A itself, and then 1 and 2. So let A and B be sets. Use examples to determine if it is true that C equals A if C is equal to the relative complement of A and B, which what I would say the best way to interpret this that I'll touch on later is C is equivalent to all of the elements that are not in B that reside within A. So if that's true, then the power set of C is equal to the power set of A, relative complement power set of B. If it is true, I'm going to prove the statement. If it's not true, find a counterexample and prove a condition that may be true. So we have a proof writing strategy in MA 383 that's super important, and I used it in this case. So the proof writing strategy, first, I did the steps. I developed all the examples, and what I found was that it wasn't true. The statement, just on its own merit, was not true. I had to modify it a little bit more to make it true. So I had to choose a strategy. How am I going to do this? Well, one of the ways you could do it is a direct proof. You could do a proof by contradiction. I showed you an example of that earlier where you assumed the opposite is true from the beginning. You could prove by cases in which you prove several different cases of the example, or you could prove by mathematical induction. In this case, I chose to do a direct proof because it made the most sense based on what I actually needed to show. I didn't need to show examples embedded in prior examples. My second step was to write down my first line. That's my let statement. Third, I had to clarify what I wanted to show. I told the reader, I will show X. And then I want to use the nuggets from my no step to arrive at my show step. And then finally, I did some quality control. So particularly in this example, I had to cite the definitions that I used, such as relative complement and the definition of power set. We explain algebraic transformations with words, not symbols. That's the best way to make sure that the reader knows the path you're going on. So here was my final proof. So proof, if C equals A relative complement B, so if C is equal to all of the elements that are not in B that reside in A, then the power set of C belongs to the power set of A relative complement B. So I needed to let X be an element of the power set of C. I will show that X belongs to the power set of A and X does not belong to the power of B by direct proof. Notice how I put the direct proof in my guide. If X belongs to the power set of C, X is a subset of C. So X belongs to C. And by the definition of relative complement of a set, every element in C is in A and not in B. So X belongs to A. Therefore, the power set of C is in the power set of A by the definition of power set. If X belongs to the power set of C, X is a subset of the power set of C. Kind of the same way I started with just the first section. Obviously, that means that X is still belongs to C. Again, by the definition of relative complement of a set, X does not belong to B. So the power set of C is not in the power set of B by the definition of power set, which was given to me by the parameters established at the beginning by Dr. Thomas. So because the power set of C belongs to the power set of A, and the power set of C does not belong to the power set of B, the power set of C belongs to the power set of A, relative complement power set of B, which is what I needed to show. And that completed my proof. And that concludes my video. I'd like to get more and get some great feedback on this proof. There were a few steps where I probably got caught up, and I'm wondering if maybe I repeated myself too much. But I'm really grateful to have the opportunity to, show and teach you more about what MA 383 is and how I'm using proof writing and how I plan to use it later on. So thank you so much for your time, and have a great rest of your day.